We're going to introduce DeMoivre's theorem, and we're going to split this lesson into two different parts. On the first part, this one, we are going to do the proof of DeMoivre's theorem. And since we're going to be doing the proof by mathematical induction and we're going to need some trigonometric knowledge, then we're going to do the proof into two sections. The first section of the proof, we are going to prove the trigonometric properties that we need for the mathematical induction proof, and in the second section we are going to do the mathematical induction proof of the DeMoivre's theorem. So to start the proof, we're going to start section 1 with the proof of these two trigonometric identities that we see right here. And the reason why we need to prove these ones is because we are going to be using the numbers in polar form, and it will be useful for us to have these identities to be able to use them freely. Let's begin with the proof of sine of the sum of two angles. We are going to base our proof on this diagram that we have here, and due to the configuration of triangles SPQ and SLR, we can see that they have two parallel sides, meaning that this angle SRL is also A. Now we're going to start the proof by writing down what the sine of A plus B is going to be. So sine of A plus B is going to be on triangle RMQ is going to be the opposite, that is RM, over the hypotenuse, which is RQ. Now I know that RM can be written as ML plus LR. So I'm going to substitute that into the sign, ML plus LR divided by RQ. Now I also know that ML is equal to SP. So I'm going to substitute that as well, SP plus LR over RQ, but I'm going to distribute that RQ. At this point, I would like to take a break and write down the values of sine and cosine of the angles individually. So sine A is going to be PS over SQ. Sine of B is going to be SR over RQ. Cosine of A is going to be PQ over SQ, and cosine of B is going to be SQ over RQ. And now going back to where I was, I notice that I have SP here, and SP is related to the sine of A, but we don't have SQ. And also RQ is related to the cosine of B, and again it's related to SQ. So if we multiply and divide by SQ on the first term, we should be able to build these two sines and cosine. So that would be SP over SQ, but we cancel that SQ by multiplying by SQ and divided by RQ. Now in the second term, we have LR, and LR we notice that is related to the cosine of A, and RQ is related to the sine of B, and the common thing between them is going to be RS. So I'm going to multiply and divide by RS, the second fraction. So I get LR divided by RS times, now I cancel that RS and divided by RQ. So this is going to be SP over SQ, that is sine of A. SQ over RQ is cosine of B, plus LR over RS is cosine of A, and rs over rq is sine of b. Similarly, we're going to do the second proof for cosine of a plus b. Based on triangle RMQ, we know that cosine of a plus b is going to be the adjacent, so that is MQ, divided by the hypotenuse, which is RQ. We know that MQ can be expressed as PQ minus PM. So we substitute and we get PQ minus PM over RQ. And we can again distribute RQ to get PQ over RQ minus PM over RQ. We know that PM is also equal to SL. So I'm going to substitute that as well. Now, what I can see is that the first fraction is PQ. PQ is related to the cosine of A, but we need SQ, which we don't have here. And similarly, RQ is related to the cosine of B, and again we're missing SQ. So now we know that the first fraction we need to multiply and divide by SQ. So we're going to say PQ over SQ times SQ over RQ. Now for the second fraction, we are going to look at the small triangle, and we notice that SL over SR is the sine of A. Similarly, this RQ is related to the sine of B, also through SR. So for the second fraction, we are going to multiply and divide by SR. So SL over SR times SR over RQ. Now PQ over SQ is equal to cosine of A. SQ over RQ is cosine of B minus SL over SR is going to be sine of A, and SR over RQ is sine of B. So with this, we have proved the two trigonometric identities for the sum of two angles. Now we can move on to stating DeMoivre's theorem and proving it by mathematical induction. DeMoivre's theorem states that for a complex number r cis theta, this is in polar form, the power of n of the number is going to be equal to the modulus to the power of n times cis of n times the argument. So we're going to prove this by mathematical induction. So we're going to assume that this is the statement Pn, and we're going to try for n equals to 1. So let n equals to 1. We're going to see what r cis of theta to the power of 1 is, and that is going to be r to the power of 1 cis of theta, and this is the left hand side. Now the right hand side is going to be r power 1 cis of 1 times theta. So this is going to be r cis theta as well. So because the right hand side and the left hand side are equal, then we can say that P1 is true. And now we can do the induction assumption. So for some value k, we will have that r cis theta to the power of k is going to be equal to r power k cis of k theta. How are we going to prove k plus 1? So we're going to start from this kth statement, and we're going to multiply on both sides by cis theta, r cis theta. So r cis theta to the power of k times r cis theta is equal to r power k cis of k theta times r cis theta. Now on the left hand side, this becomes r cis theta to the power of k plus 1. So that side is already done. And the right hand side, we can put together the two r's that we have. So r to the power of k plus 1. And then we have cis of k theta times cis of theta. Now to work this out, we should substitute the definition of cis theta, and that is going to be cosine of k theta plus I sine of k theta times cosine of theta plus I sine of theta. So if we distribute this, we're going to get cosine k theta times cosine theta minus sine k theta sine theta plus, now we're going to have all the terms that have I, so we're going to have it out as common factor, I sine k theta cosine theta plus sine theta cosine k theta. Now if we look at this, cosine k theta cosine theta minus sine k theta sine theta looks like a cosine of k theta plus theta. So this is cosine of k theta plus theta plus I, and sine k theta cosine theta plus sine theta cosine k theta is sine of k theta plus theta. So sine of k theta plus theta, and this is equal to r power k plus 1 times cosine of, and this can be written as k plus 1 theta plus I sine of k plus 1 theta, which happens to be cis of k plus 1 theta. So we have just demonstrated by mathematical induction DeMoivre's theorem is true for all exponents of the complex number set.